Okay, good morning. How is everyone? Good? Having a good time? That's great. So we will spend a few minutes talking about some fundamentals of ecological modeling, and specifically soil-water plant interactions. How many of you had any class in soil physics? No one? A class in soil physics. Okay. And that's okay. So let me start by saying that two fundamental units of understanding eco-hydrological processes. One is the soil moisture and soil moisture dynamics. That is influenced by soil physics and understanding of soil physics. And second one is the evapotranspiration. And Professor Vamsi talked a lot about evapotranspiration, crop water coefficient, etc. So other critical component is really the soil moisture. And soil moisture that in combination with evapotranspiration drives the hydrological processes. So you get your next job, and one of the first assignments is to review a report, where in that report someone comes and presents the evapotranspiration numbers for the river basin that you are in charge of as 10 millimeters per day. 10 millimeters per day of evapotranspiration happening. What will be your response?
It's impossible.
It's impossible. Why is that impossible?
It's a huge difference. It's a big difference.
So it's impossible, it's a big number. What is a reasonable number? How much does it rain in Telangana? 700 to 1500 millimeters, right? So let's average it, 1000 millimeters. Given 1000 millimeter of precipitation or rainfall that happens, how much evapotranspiration can you expect in a day on an average?
40%.
I can't read your lips. Speak up.
60%.
Right, so give me a number in millimeters per day. Right? I want you to have, not just from this class, but as you go through your research, your degree, you should develop an intrinsic common sense for what numbers make sense. One of the most common complaints from my students was that they will bring a figure and I'll take a look at it and tell this is wrong. And they will ask me, what is right? And I can't tell what is right, but I know it is wrong. Just like you knew that 10 millimeters per day is the wrong number. You may not know what is the right number, right? And that's where it comes from. So how many millimeters in a day can you expect evapotranspiration on an average? And if it is outside, you say that this is wrong number.
About 2 mm per day.
Yeah, so maximum 2 millimeter per day, right? 1000 divided by 365 if it is raining every day. And 65% of that on an average is evapotranspiration. Somewhere between 1 to 1.7, 1.8. So even on the days when it is actual evapotranspiration is close to potential evapotranspiration, it is not going to exceed 2 millimeters per day. And so that's one of the points I want to make. But let's spend some time looking at the soil water plant interactions. And what I expect you to know by end of this lecture is you should have a comprehensive understanding on different properties of soil. I'll just scratch surface on the soil physics. It's a semester-long course, but and we are not going to be able to do that, but some appreciation for what soil properties impact ecohydrologic processes. You should be able to describe the process of soil water dynamics and plant water uptake, and have an understanding of the role of vegetation in ecohydrological cycle and processes. So these are the learning objectives. Soil moisture is the fundamental unit, and all the if you look at the ecohydrologic models, all the calculations, all the entire model is usually, it starts with a water balance that is driven by soil moisture content. Even in the SWOT model, that is the fundamental equation, right? That's the first equation. Soil moisture as a function of all other variables. And that's what SWOT is tracking, and that's where everything else is built. How much is the biomass production, how much is the nutrient cycle, runoff, etc. And it plays a key role in hydrologic cycle, particularly within the soil plant atmospheric continuum. The vegetation that is supported by soil moisture dynamics, it influences local climate by influencing evapotranspiration and humidity and temperature. And soil moisture dynamics is driven primarily by three forces. You know, one is the gravitational forces, how much of that will percolate and go into shallow or deep aquifer, how much will be evaporated, and how much will be lateral movement that might appear as a surface runoff or will continue to move downhill. Now, let me ask another fundamental question. Why plants have transpiration? Why do plants need to transpire? Very basic question. Yeah.
Because of heat, they don't dry out. That's why they release some water, so it will evaporate and cool down the system, just like heat here.
Absolutely. The only function is to keep plants cool. And if they stop transpiring, the temperature goes up, they wilt and they die. If you are running outside and if you stop perspirating, you will collapse because the body temperature will really go up. So but because that happens, that plays a role in bringing the nutrients up in the plants that supports the biomass growth and development. So there are soil properties that you should pay attention to and you should know. This is just to get you started. This is by no means making you an expert on the soil physics. But I want you to go back and if your research involves anything to do with the soil properties, whether directly or indirectly, spend some time understanding the soil physics. And there are two fundamental principles are properties that become important. One is the soil structure, other one is soil texture. Right? Soil structure is how individual particles are assembled together. Right? Unless you take any core of soil sample anywhere, you go and take a core outside in the lawn, and there will be a certain arrangement of sand, silt, and clay. And how those sand, silt, and clay are arranged together to make that soil core defines the soil texture. And it can happen in different patterns, and that affects the hydrology, that affects how well plants are able to access water, how long plants are able to access water, or how much water can be held within that soil core. So these are the different examples, you know, where you can look at. If it's all sandy soil, if it's all sand, then there is a lot more porous space. The there is lot more room to hold water, but the water is not held in place, right? The water holding capacity of sand is very little. Most of that will drain because of the gravity. Sand particles have smaller surface areas, and because they have smaller surface areas and because they are electrochemically neutral, they hold very little nutrients on the surface, as opposed to clay particles that have much larger surface area, and they are negatively charged, and therefore they can hold positively charged nutrients close to the surface. And so you see how it works and how it affects. On the other hand, clay soils have, because they are finer particles, they are aggregated really densely together. There is, the infiltration rate is much smaller, and there is a lot more runoff that happens. And then you may have seen, you may not have seen this triangle. It is in every soil physics book, that gives the texture of a soil depending upon the percentage of sand, silt, and clay. And that tells us about what to expect hydrologically, depending upon whether it is a clay loam or silt loam or sandy soil or clay soil. You can look at the percent distribution and you can guess a lot about what kind of hydrologic response you should expect, right? So when you're looking at your model and you're looking at infiltration or runoff or percolation, or you're looking at ESCO and EPCO parameters in SWOT, and if it is not making sense, you should go back and look at how soil is described in the database of the model and whether it is making sense or not. You know, that's where, again, the common sense should come into play. The texture is very important because it has a big influence on hydrology. It determines the amount of water that the soil can hold. It determines the rate of water movement through soil, so it determines the infiltration rate as well as percolation rate. You guys understand the difference between infiltration and percolation, right? Infiltration is when it's entering the soil profile, and percolation is when it's moving within the soil profile. And those rates are different depending upon the moisture content of the soil. And then workability and fertility of the soil, because depending upon the surface area of the soil particles, they have different ability to hold nutrients. So we talked about sand that is well aerated but does not hold much water, as opposed to clay that holds a lot of water and better at supplying nutrients because it's negatively charged. However, there is less infiltration and more runoff that happens. So other important concepts is the water retention, how well it can hold water. And that is influenced by soil texture and soil structure. Again, sandy soil have poor retention capability and clay soils have greater retention capability. It also determines the hydraulic conductivity, right? And if you are working to determine what is a good groundwater recharge zone, are there areas here in a watershed that is designated as groundwater recharge zones? It's very common in the US where you are driving through and you will come across a board that says groundwater recharge zone, please do not dump. And usually you can have a good guess about the soil properties in that area. So it will be sandy loam soils, you know, most of the time. It will be mostly forested. If it was completely sandy, you know, it won't be able to support a good forest growth or forest cover. And you can guess a lot about hydrologically what is happening. You can expect a lot less runoff coming,
and a lot more infiltration and percolation that is going to recharge the groundwater, right? So that's where your professional knowledge can start to come into picture about how to delineate suitable areas depending upon what you want to accomplish. Hydraulic conductivity depends on the moisture content, and two important concepts are saturated hydraulic conductivity and unsaturated hydraulic conductivity. And then soils with high conductivity allow for rapid drainage, whereas those with a low conductivity can lead to waterlogging. You see that at play during cricket matches when it rains, right? And how long it takes to dry the ground without having those super soppers. So if you are hired to design a cricket stadium, you can really design it in a way that the play can resume very quickly after the rainfall event, knowing the soil physics and knowing how the soil works. So putting it all together, the soil structure, retention, and hydraulic conductivity determines how soil is interacting with the water, and in turn how that is supplying the nutrients and water for the plant growth. They also impact groundwater recharge and surface water availability, and these interactions become even more crucial in the context of changing climate. You can start to see if there are areas where there is more clay soils or clay loam soils and precipitation events are becoming more intense. Even without presence of urban areas and built up areas, you can expect more flooding to happen because they will poorly conduct water through percolation. And well-structured soils promote optimal water infiltration, so the concept I talked about, also supporting biodiversity and ecosystem stability. It also supports the microbial activities that happens within the soil. How many, give me an idea, I love asking this question. So you take 1 gram of soil and you put that under microscope and you count all the microbes that are there. Give me a number, some sense. 1 gram of soil. Lakhs, yeah. Much higher. It will be somewhere from billions to trillions. Yeah. It's amazing biome. I mean, it's really amazing, and that's what drives most of the chemical reactions. You know, chemical reactions don't happen by itself. It's the biological properties that are driving most of the chemical reactions that are happening. Other two important concepts to understand. One is the soil water capacity, and soil water capacity is determined as a difference between fill capacity and wilting point. Fill capacity is if you take a column of a soil and saturate it and let it drain through the gravity. Once all the gravitational water is taken out, how much moisture is held within the soil column is the fill capacity. And then if you continue to dry that, there comes a point where the water will be held so tightly with the soil particle that plants won't be able to extract that anymore. And that is the wilting point, right? At that point, the soil is not completely dry, but the water content is so little that the roots are not able to extract it. And so the difference between fill capacity and wilting point is available water capacity for the soil. these are the numbers. As you are applying SWOT or any other eco-hydrologic model, you should be looking at, and you should be having a common sense of, whether those numbers are right or not, depending upon the soil type that you have got in your water set, depending upon the soil properties, and you should be able to figure it out even before you attempt to calibrate the model. Right? So once you set up the model, don't jump onto calibration right away. Go back and look at uncalibrated results and components of the uncalibrated results, and make sure that they are making sense to you. Otherwise, you will be overcompensating some of the parameters, and your calibration may result a right number. You may be able to match the stream flow, but you will come to a right conclusion for a wrong reason, and you don't want to do that, right? So always go back and look at uncalibrated model result, and go back and look at individual components and see whether those are making sense or not. It's possible that soil is not represented well, or some of the parameters to start with are not right, and you know what to fix first. So that is always a good modeling practice. We talked about permanent wilting point. Plant water uptake. So the difference between fill capacity and permanent wilting point determines the water holding capacity, and that plays a principal role in water transfer in soil, plants, and atmosphere. You know that 65% of that goes back to atmosphere as evapotranspiration. Then capillary structure within the soil also determines how well water is moving up and down within the soil column, and how well the nutrients are brought with water as they move through capillary structure within the soil. So most of the models, including SWOT model, will give you an idea about different stresses to plant growth. And the slide says two principal stresses. There are actually three principal stresses. What is not there is temperature. So there are three principal stresses to the plant growth. One is water. Second one is the nutrient that are needed to support biomass production. And the third one is temperature. If the temperature is too high, and it's not, it can have the growth stress. SWOT will give you all three stresses. And very few people are able to, not everyone is able to look at it. Very few people actually look at those stresses and see whether it makes sense or not. So if you're applying your fertilizers, and if the rainfall is making sense to you, and if SWOT tells you that there are 300 days of nutrient stress, you know something is wrong somewhere. You don't know, you may not know the right answer, but you know that it is wrong. And again, before you jump onto model calibration, go back and take a look at it. Is it making sense? There will be some days of nutrient stress, there is no doubt. There will be some days of water stress. But having that idea is going to be very important. If you look at the water stress, right, look at why there is a water stress. Is it driven by the soil type that is there? Is it driven by how long it has been since it rained last? And looking at the soil moisture balance, looking at precipitation pattern, you should be able to figure it out. Then what it does and what happens is stomatal closure, and then plants start to wilt. Nutrient stress, it occurs when essential nutrients are not there, NPK are not there, or carbon is not there, and it can result from factors like poor soil fertility, imbalanced nutrient supply, or poor nutrient uptake. Most of the time, when you initialize the model, it takes the default values from the database. How many of you have used the SWOT model? Have you looked at the initial values of the soil nutrient content? Yeah, yeah. So go back and look at the database, right, and see if it makes sense. See if the carbon content makes sense. And if it is not making sense, fix it even before you run the model for the first time. Because if you don't do that, even after 2 or 3 years of warm-up period, the model may not be able to come to a steady state where it is actually representing the reality. And then when there is a nutrient stress, it will affect the biomass production, different things will happen, the growth will be stunted, there won't be full LAI, there may not be optimal photosynthesis happening, and your total biomass production will be less than what actually happens. So has anyone looked at the biomass production in the SWOT model for your land use? It drives the hydrology, right? Now you know that it has a very important impact on the hydrology in the water at the watershed scale. And so when you run the SWOT model first time, that will happen when? Today, tomorrow sometime? Tomorrow. Go back and look at the biomass and ask the question, is biomass making sense? And for that, you need to know what is the number that should make sense, right? So you should intrinsically know, depending upon the crop that is being grown, what is the expected biomass and what is expected yield. There are two terms there. One is the biomass, another one is the yield. What percentage of biomass is actually harvested, and that becomes the yield. And I don't know the numbers for India, but you should know those numbers for India. I know the numbers for US quite well. So if one of the land use is cotton, or if one of the land use is maize, you should know what is the biomass for maize or cotton and what is the yield for that. And see whether you are starting in a right way or not. Because if you are getting that wrong, chances are hydrology will be wrong too, because you're not accounting for photosynthesis that is happening, you're not accounting for evapotranspiration that is happening, and soil water plant interactions in a realistic way. So I hope that this will make you a better scientist by looking at not just focusing on the stream flow like everyone else in the rest of the world does, but going back and looking at the individual processes and making sense out of it. So ESCO and EPCO and number of other parameters that determine how well the water is moving from how deep in the soil and how you need to relate the values. Don't go back and change it in a random way, right? We are not trying to put a number of monkeys to write Shakespeare. That's not the goal here. Other important concept to know is the plant water use efficiency. How much biomass can be produced for a unit amount of water that is supplied. And when you're doing the watershed management, and when you're looking at ecosystem services, and when you're looking at what really needs to be done, and if your objective is beyond just the hydrology, knowing water use efficiency becomes very important. So I spent some part of my career in Arkansas, in US. It's one of the states in the central south part of United States, if you're familiar with the map of US. And to give you another reference, President Bill Clinton came from that state. I was working on a project looking at watershed management in general. It was much more than that. And we were looking at groundwater depletion because of the agricultural production in Mississippi Delta, the region along the Mississippi River. Mississippi River is one of the largest rivers globally. And so this delta region, there is a lot of rice production that happens. And we were looking at how groundwater is being depleted because of the land use that happens and what needs to be done. So I started engaging farmers and talking to why they are doing what they are doing. Does anyone know the water use efficiency for rice? We all eat rice every day. How many kilograms of water does it take to produce a kilogram of rice? Someone said something. 5,000 liters per 1 kg of rice. That sounds right. You know, somewhere between 2,500 to 5,000. Yeah. So it's in that range, right? The water use efficiency is very poor for rice. Does not mean that rice should not be produced. It means that rice should be produced where the water is there. So I asked the question, where do you sell your rice? Who buys your rice? And I was not prepared for the answer I got. Anheuser-Busch. Do you guys know the name? Come on, someone needs to know the name, Anheuser-Busch. It's one of the largest beer making companies in the world. And Anheuser-Busch buys Arkansas rice for their beer production. Does it now make sense in a water limited area to produce a crop that is so inefficient from water use efficiency point of view? So those are the questions, you know, when you bring the eco-hydrologic perspective, you can start to ask. So what role vegetation plays in eco-hydrological balances? Vegetation plays a crucial role in shaping the eco-hydrological processes because plants interact with the soil and water to regulate local climate, and plants interact with soil and water to regulate, well, it happened twice, improve soil structure and promote sustainable growth. And they are controlling evapotranspiration, which is the most dominant part of hydrologic cycle. They also play a role in what happens to erosion and sedimentation. We talked yesterday, 1918, we knew that a forested catchment produced less runoff than another catchment with 1/3 tree cover. But also, erosion is a lot less. There is a movement in US that has happened quite successfully. There is a movement in India that is happening, and it has become a global movement. Save the soils by Sadhguru, right? Do you all follow that? And the movement in US that started in 60s and really gained momentum, it's called cover crop. So because of the climate, Usually there is only one crop that happens in most of the US, except the southern part. Northern part where I live, where I lived before at Purdue, there was only one crop in the summertime. Rest of the time it's too cold to produce anything. And so the soil is sitting barren. And when there is a precipitation or when there is a snow melt, then there is a lot of erosion that happens. It erodes the top layer, which is the richest in organic matter. And it's multi-billion-dollar problem. So, NRCS, Natural Resources Conservation Commission, came up with this movement that let's plant cover crops. And cover crops are widely adopted now. What they do, that they protect the soil. Because there is a cover, the runoff is less, infiltration is more. If there is a runoff, they act as a physical barrier. The velocity of the water is less, and because velocity is less, kinetic energy is less, there is less erosion that is happening, and therefore the soil is protected. And that's what this figure depicts, that how they are stabilizing soil, how they are enriching the organic matter content, how they are improving the soil fertility. If the cover crop is also leguminous and fixing nitrogen, then you get that credit for the next year's crop, and you need to apply less nitrogen. Vegetation also plays a significant role in soil moisture dynamics through various mechanisms, such as by improving the soil structure, they are improving the infiltration that takes place, and there is less runoff. Canopy interception, Professor Vamsi talked about, and type and density of vegetation determines the extent of soil moisture retention in the ecosystem. The deep-rooted plants, they can access groundwater, providing resilience during dry periods, while shallow-rooted species rely more on surface moisture. And then there is this concept in some ecosystems called hydraulic lift, where deep-rooted plants are bringing water to support the shallow-rooted plants. So, to summarize, you really need to understand the soil physics if you want to be a good scientist. You spend some time understanding the soil physics, because the soil physics plays a dominant role in ecohydrology. How it interacts with water, how it interacts with the plants, and that is continuous, right? Plants affect what happens to the soil. But by understanding the soil physics, you will have an intrinsic ability to improve the models right away without having to go and over-calibrate a model. These will also make you understand what needs to happen in a watershed management context, and how you can come up with better decisions, or if something happens, how you can explain that from soil physics point of view. And having that will really enable you to come up with the solutions that will be more sustainable for the environment.